Okay, so this is getting started with the technical content of language processors. So a key question here is, what is a language processor? And essentially it's something that takes source text or input in one language, does something to that data or that input stream, and produces output in possibly another language, possibly the same language. So some language processors will have the same input and output language, but often we'll be thinking about a sort of higher level input language and a lower level output language, for example in the case of compilers. So this is not a compiler's course as such, it's a language processor's course, and a compiler is seen as a special case of a language processor. So we will be looking at some of the compiler specific stuff towards the end of the course, and in particular, what does it mean to lower a language? So how do you go from a high level language like C to a low level language like assembly? Just like we saw in architecture, the languages are a kind of interface or API. So you can specify a language without actually having to specify how that language is implemented. So for example, the C or C++ language specifications are books, essentially, and there can then exist multiple actual implementations of those languages. So just like the MIPS ISA is a specification, there are lots of implementations. A language is a type of interface or API. So in terms of what a language is, then there's actually a lot more types of languages than you might think of. So even with human language, there are different representations of language. So I'm speaking now, which is one form of language. I'm looking at, and you're looking at, written words, which is another kind of human language. There's actually a visual language going on in these slides. That, for example, I've chosen to use red at the top of the slides to represent the title, and that's become a kind of visual signpost, or as part of the visual language of these slides. There's also different sources of human language. So there are formal specifications. So in some sense, the English grammar is partially defined somewhere. There's an accepted definition of it. There are de facto languages. So, for example, that red is title thing is something that you're picking up from these slides. You didn't have to be told it, you are learning the visual language of the slides. And there are also private languages, although don't need to worry too much about them. And the reasons we use languages are obviously many and varied. So sometimes it's to communicate or cooperate, sometimes it's to transmit information, sometimes there is essentially no purpose to language. The languages that we're going to look at are quite specifically text-based languages. So in this context, text is simply a sequence of characters or bytes. Sequence is important here. It means that there is an ordering on the bytes. One character occurs before another character, and it's important that it occurs before another character. So the kinds of text that we'll be looking at comes from places like files, which is an ordered sequence of bytes or characters, network streams, which again has an order to the data going through it, things like the output of a program, so sort of standard outs and printf produce sequences of characters. We're interested in both formally specified and sort of implicit or de facto languages. So something that we're going to look at in quite some detail is the case of C. So there is a formal C language specification. The expectation is that you will be able to compile that C language. There are also other situations where the tools that we introduce here are useful, where we say, here is some data, and it's kind of up to you to work out how to turn that data into structured data and then do something with it. In terms of the uses that we're thinking about here, the three main uses we're thinking about are language as a form of instruction. So a C program is actually instructions for solving a problem. Communication is also something we're interested in. So movement of data between places. It doesn't come up quite so much here, but you're looking at this in networks at the moment. The streams of bytes are a good way of moving data from one program to another, or from moving data from one node to another. And the fact that it's a stream means it's very easy to move these things around. We also sort of implicitly use langages for persistence. So your C programs will often sit at rest on a computer in a file. So there you're essentially moving information from now into the future by having it on this persistent file. So there are other uses of languages in computing, but those are the three that we're mainly interested in. So as an example of what it means to sort of work with de facto or empirical language processing, here I've got three fragments of text, but actually we can only see one character from these pieces of text. And obviously we can tell almost nothing about these languages. All we can see is one character that doesn't give us enough information. If I take pairs of characters, I still don't really have enough information to even guess what these languages are. I don't know if they're human or computer-based languages. But once I've actually got enough characters or symbols that I can start making tokens or words, then I can start to make some kind of guesses about these things. I still have no clue what these languages are, but it's starting to make a certain kind of sense. But in order to really start understanding it, I need to see not just groups of characters, I need to see groups of words or groups of tokens. So in the top example, we can now see the entire thing and from the start. So we can see that from the first character we can read that as what is the point. That feels like free-form English text. It doesn't look like a particularly computing language. The middle one, we can see that there's some kind of imperative C-type statement, so we can make a guess that this is some language that inherits from the C family. In the bottom one, well, we've got a couple of words or possibly words, but we still can't really tell exactly what's going on. We need to be careful as we introduce more, because this middle example where we thought, well, this looks like a program, if you put the right characters before those characters, or the right tokens before those tokens, then it can actually change the meaning. So that speech mark before the for is actually changing the meaning of those characters that follow. So now it looks like it's a variable that's been assigned a string literal, rather than that being the code itself. So trying to be a bit formal about this, the kinds of things that we'll be looking at is this sort of hierarchy from the lowest level primitives of language up to the highest level overarching meaning giving properties of languages. So from our point of view, languages at the sort of primitive atomic level consist of characters or bytes, or it could be Unicode points, and these are the indivisible parts of the language. So you can't take the letter A and split it up. It's either an A or it's not an A. Tokens are the next level up. We're actually grouping the characters together, and here we're actually mapping individual characters into meaningful but still low level words or tokens. Syntax is then taking those tokens, those sort of fundamental things within the language, the words within the language, and talking about the ways in which they can be ordered. What can follow what? Can I have a verb then a noun, or a noun then a verb? That kind of thing. Taking that slightly further, grammar is the sort of stricter version of syntax. It's actually the very rigorous specification of exactly what order tokens can appear in, and things like nesting and sort of recursively defined constructs. One level above that, and something that goes beyond basic grammar, is semantics. And that's where we actually say, well, I know how to get the structure out of this sequence of characters, but what does it actually mean? How do I usefully interpret this structured data that I've extracted from this stream of characters? So along the bottom here, we've got three examples of things kind of breaking down at these different levels. So looking at the leftmost example, we've got a clearly broken program here, and this is, I would argue, broken at the token level, or what's called the lexicographic level. So we've got this token rect hash run, which is clearly not something that's forming a valid C token. If hash appears in like this, hash needs to appear at the start of the line. So there's clearly some kind of token-based error. If we go to the middle one, then the tokens themselves are all quite well formed. So we can see int, which is a keyword, main, which is an identifier, f, which is an identifier, int, which is a keyword, brackets, all of these things. But there's a problem here in that the meaning of this grammatical level doesn't make sense, because we know that a parameter list of a function should consist of a type, then some kind of name or some kind of declarator. So this is composed of valid tokens, but is actually combining those tokens in an invalid way. Finally, on the right hand side, we have something that is grammatically correct. So that is syntactically legal, it's sort of nested correctly. But if I think of the semantics of that program, then here we are creating a void pointer which is initialized to null, which has special meaning within C, and then we're then trying to dereference that. So dereferencing null is undefined behavior. So rather than being semantically incorrect, this is more semantically undefined. We don't know what it will do, but we know that it's not well defined. So thinking about the kinds of languages and language processes that you use, there's all of these things related to code, compilation, execution, all of these things. So an assembler is a simple program which takes assembly as an input language and lowers it to the binary object code. It may do slightly more complicated things as well, but it's a relatively simple piece of software. In comparison, a compiler takes something that's much, much higher level, so C++ or C or some other high-level language, and takes it all the way down to really quite low-level assembly. It's actually only one step away from object code. But we also have lots of other types of language processes. So at the start of this term, you were developing a cache simulator, which has an input language that I defined and also has an output language that I defined, and also has well-meaning semantic, well-defined semantics. There's a bunch of other language processes that you use kind of every day. So this thing here is a language processor. There's all kinds of languages going on inside. There's bits of HTML, there's JavaScript in here, there's comments, there's all these kinds of things. And there's actually lots of languages layered on top of each other. And things like web browsers are, well, critical to modern day user interfaces. I included Arduino here because often you can view input and output as forms of language processing. So if I have an Arduino, it could be processing a stream of sensor data, for example an I2C bus producing heat levels, and then sending that or interpreting that over HTTP as an output stream. So if you think of a web-enabled thermometer, it takes in a stream of symbols in some kind of temperature stream and produces HTML or something that other people can look at, which is a different form of that data.